All right, so today, let's look up here, please. Okay, today we're going to look at section 4.2. The assignment's up, but you wouldn't have really probably known how to do some of this stuff. So let's go through it. What we're going to talk about over the next few days is, are we about got that wrapped up there pretty quick? Okay. So the next few days we're going to talk about congruence relationships in triangles, right? Just so you kind of have a little idea how this is going to unfold. We're going to start talking about what it means for two triangles to be congruent today, and we're going to have kind of an inefficient way of showing that triangles are congruent. We're going to improve upon that and come up with better ways, easier ways in the next few days. But for today, we'll just kind of talk about what this all means. So we want to be able to identify congruent figures and corresponding parts, and we even want to maybe be able to do a little bit of proving some things. Okay, we'll look at both of those today. Quickly, let's remind ourselves what it means in geometry for figures to be congruent. Figures being things that we can draw on a piece of paper. Things are congruent in geometry. Figures are if they have the same shape and size. So for example, if we look at all these red shapes, they are congruent because same shape and size. What does that mean? Well, if those were cardboard cutouts, it means that I could pick up one of these and I could reorient it. That means I could twist it, I could even flip it around front to back if I wanted to, and set it down on top of another cardboard cutout, and they would overlap perfectly, right? We see that's clearly not the case with the blue ones here because the blue ones are all different shapes. So they're obviously not going to overlap perfectly. What about the size part? Well, if I were to take one of these cardboard cutouts and let's say we make a photocopy of it, but in the photocopy we're going to, a color photocopy, we're going to either enlarge it or reduce it. So it's the same shape though, right? Is it going to be congruent? It's not, because then it's a different size, right? It is a relationship that's interesting to us. We'd say that if we did that second thing, if we took a photocopy and either reduced or enlarged the picture, then we'd end up with a new shape that is not congruent but similar to the original. And we'll get to that later on in the class. But for now, we're just talking about congruent. So it wouldn't be congruent. Okay, so here's something that you got to be really aware of, though. And this is an easy mistake to make in geometry. If you have two figures that are congruent, then there has to be a one-to-one correspondence between all of the parts. Okay, that has to be true. So if two figures are congruent, then and I overlap them on the board, then the corresponding parts would also all have to be congruent. Well, what are the corresponding parts? Well, for shapes, that we're going to be talking about, for triangles, for example, or later on for quadrilaterals or other polygons, the parts are just the angles and the sides, right? So the angles, corresponding angles and corresponding sides would also be congruent then. So let's take an example here. We can see that we've got these two triangles, and not because they look congruent, but because we're given a bunch of information on the drawings that tells us there are some congruences there. We can line these things up and we can show that the triangles are congruent. So does everybody see here, well, like what is angle A is congruent to what angle in this other triangle? Angle P. And why is that in our drawings that we can see that's the case? Okay, good, because the angle congruence marks match up, right? We've got the two arcs for A and the two arcs for angle P. So that's our way of saying that those angles are congruent, right? We get one arc for B and one arc for Q, so we know angles B and Q are congruent. 3 arcs for angle C, 3 arcs for angle R, so those are congruent, right? What about the sides? What's an example of, okay, like side AC, for example, is congruent to side what? PR, okay? And we know that because it gets 3 hashes and 3 congruence hashes, right? Or dashes, whatever you want to call it, okay? So the left triangle is congruent to the right triangle. There are a bunch of ways of saying the left triangle. Somebody name the left triangle for me. Triangle what? ABC. What's another way of saying the left triangle? CBA. What's another one? BCA, BAC, there's a bunch of ways, right? What's a name for the right triangle? PQR is one, sure. What's another one? QRP, a whole bunch of them, right? So it seems like there ought to be just a ton of different ways of saying that the left triangle is congruent to the right triangle. There are a few, but not as many as you might originally think. Because when I write a correct congruence statement, I always have to line up the order of the vertices that I write in one triangle has to match up with the order of the corresponding vertices in the other triangle. So for example, if I write down triangle, whoops, oh, what's that? Oh my gosh, where did that come from? Oh, is this thing all messed up? Oh, this is all right, this is gonna be a little strange.
Hey, Mr. Oya,
Yeah.
can I read the restroom?
Yes, you may. So if I write down triangle ABC is congruent to, and I want to write a congruence relationship, how do you think I have to write the other triangle? I really don't have any choice now.
PQR.
It's got to be PQR because I have to have, if A goes with P and B goes with Q and C goes with R, then I have to write the corresponding order. So that's going to be A goes with, what do we say, P, B goes with, you see that the pen doesn't match up with mine? That's going to make this really difficult for me. Q, so that goes with Q, and then C goes with R.
Can't you just hit that little
Yeah,
fire
yeah,
thing?
yeah.
Let me try it. I don't know if it's going to work or not, but oh my gosh, we'll try it. This thing right here?
Yeah, just hold it.
Okay.
Touch it.
Tap, and then tap.
Now what do I do?
Follow the instructions.
Follow the instructions.
Hold your pen for 2 seconds.
Oh my god.
So where's the,
Press and hold it.
Okay.
Okay,
Tap that.
Yeah.
There we go. Okay, like a cool game, all right.
Yeah.
We'll try this.
Have you ever done it before?
Yeah, I have, but it seems like it didn't work when it did this last time. Because it's, what I had to do is turn everything off and turn it back on, but maybe hopefully I'm wrong. Okay, well, seems to work, good. All right. So, what if I call this one, okay, you finish this statement for me. Triangle RQP is congruent to triangle what? Say it again? Yeah, it's got to be CBA, doesn't it? Right? Because C goes with R, B goes with Q, and A goes with P, right? Does that make sense? So we have to line up the corresponding parts, okay? Another question you might be asking is, how do you input this in Moodle? How would you write triangle in Moodle? Because, you know, that's a symbol, and in Moodle, a lot of times, we don't have access to the symbols. So what do you think? What's your intuition tell you? How do you think you'd probably write triangle ABC?
Type triangle and then put some.
That's it, triangle in parentheses, very good. So you'd write like this. Triangle ABC, for example, right? Okay, good. Okay, so there's more than one way to write a congruent statement, but you have to make sure that to list the corresponding angles in the same order, what we just talked about. Okay, so what about this one? On your paper, write down a congruence statement for this one. Okay, Savannah, what'd you get for your congruent statement? Triangle,
FET.
okay, triangle FED is congruent to,
TSR.
good, TSR. Does everybody see that? TSR. Let's look at Y. Okay, triangle, she started with vertex F, right? Well, angle F, because it's got 3 loops, congruence loops, goes with angle T, right? So if F is first, T has to be first. E has 1, S has 1, so E goes with S, and then we're left with D and R. Okay, make sense?
Yes.
It's easy sometimes to think, oh, well, these are just, folded versions, and so F goes with R, but you gotta look for the congruence marks, right? Okay. Okay, this guy. Let's see. Okay, this kind of problem. Now, we're pretty good at these. We've had a lot of practice at these. But now we've got a situation where we're going to solve for some variables. Now, something looks a little different here, and let me explain. We're not going to deal with this a lot now. Later in the class, we'll deal with expressions like this. What do you think that means? Well, once we get on to shapes that are more complicated than triangles, polygons, shapes that have sides, a lot of times we don't want to write a symbol because the symbols start to get just too hard to draw. Like if you wanted to draw an octagon, drawing that little symbol for an octagon would start to get a little bit cumbersome, right? So what we do instead is we just make a list of all of the vertices in order. That's it, right? So for example, this NPLM tells us that this is quadrilateral NPLM, okay? We're told that is congruent to quadrilateral looks like maybe let's do that. Quadrilateral EFGH, right? So that's telling us which are the corresponding angles and the corresponding sides. Can anybody tell me what is the side that corresponds to side NM? It's EH, yeah. And it's almost easiest to see it just in the congruent statement, isn't it? Right? Because look at this. If I go side NM, well then I'm going from the first to the fourth, right? And so I must go EH over there, right? See what I'm saying? We just follow the same pattern in the second shape that we do in the first shape. Okay, so then we want to solve for x. So just like we've always done now, our goal is we have to come up with some kind of a geometry relationship that we can use to build an equation. So what do we think here? Abby, do you have an idea? If I want to solve for x, do you see a geometry relationship that might be useful to us here? Okay, good. Right, so we want to set the lengths of two sides equal, don't we? Because it looks like x is telling us it's a part of the length of a side on this one, right? So it looks like it's on side, what is that side? How do we label that? GH, okay. So side GH must go with side LM. Okay, good. So those measures would have to be equal, wouldn't they? So what equation is that going to give us then?
2x minus 3 equals 8.
2x minus 3 equals 8. Very good. Okay. What are the two steps in order, Bailey, that we're going to have to use to get the x by itself?
Plus add 3 to both sides.
Add 3.
And then divide by 2.
Yep, divide by 2. Good. So if we add 3, we get what? 2x equals 11. Divide by 2, and what does x equal? Well, if we want to make it a decimal, it's just 11 halves. If I want to make it a decimal, I can make it 5.5 if I want to. That's fine. Good. What about solving for y? How are we going to solve for y? Tyler, do you see a relationship that allows us to solve for y here? It's like y is part of an angle, doesn't it? Yeah. So y is a part of what angle? How would you label that angle? E, okay. So angle E must correspond to, in the other shape, to angle, which one? Look at the congruent statement up here, and that's probably the most helpful. And there you go, good. Right, those are corresponding places, right? So, because sometimes it's hard to see on the picture. So then, what's the relationship we're going to get? Okay, so what's that going to look like in terms of an equation?
7y plus 9 equals 72.
Okay, and what are the two steps, Lacey? What are the two steps in order to solve for y?
Subtract 9 on both sides and then divide by 7.
Good. Subtract 9, divide by 7, so I get 7y equals what? 63. And then divide by 7 and get what? Yeah, good. Y 63 divided by 7 is 9. So we got it. Good job. Okay. Good. Okay, and there's what we did. What about, okay, oh, here's something we want to come up with. This is another theorem. And just so you know, I have updated those two parts at the top of the geometry page where it's got the new Moodle symbols. Well, I updated those to include how you do triangle. And then the reasons, I've updated the reasons to include all of the new reasons from chapter 4. Okay? Here's one of the new reasons that we have, for example, if we're going to do some proofs. This is a real common sense theorem. Think what this says now. If angle A is congruent to angle D, and angle B is congruent to angle E, then doesn't it make sense that angle C must be congruent to angle F? Okay, somebody justify that.
Because if they're both the same, measure, like number-wise, then the other one have to add as one.
Okay, there's the key. They have to. We know that all of the interior angles, the measures of all the interior angles in any triangle, always add to 180, right? So doesn't that mean if angle A is congruent to angle D, then those measures are the same. Angle B is congruent to angle E, then those measures are the same. Then doesn't that mean that there'd have to be the same amount left over in both triangles for the third angle? So they'd have to be congruent also, right? So that's kind of a good deal. If we know that two angles in one triangle are congruent to two angles in another triangle, we get the third for free, right? The third angles must be congruent. We just call that the third angles theorem. Okay, so let's use that. Let's do another, let's do one like this. Okay, so we gotta solve for x here. So take a second and just stare at this. Think about this for a second. How are we gonna do this? We gotta somehow come up, use a geometry relationship that lets us come up with an algebra equation to solve for x. There's maybe a couple things going on here. Okay, tell me one thing that might be useful here. Shop, tell me something.
Like look where the numbers are?
Well, you decide. I mean, so if we're going to solve for x here, what's something that might be? There's a bunch of stuff that might be useful. Maybe it's not, but just tell me something about that.
2x plus 3 is in the left corner. If you flip the thing over, I don't know.
Okay, yeah. So now there's something. Let's look at that. So this angle right here, 2x plus 30, is an angle in the right triangle. Would that angle be congruent to any angle in the left triangle? Does this angle have to be congruent to some angle over here? Which one? M, okay. How come?
Because it doesn't have a.
Oh, okay, good, because look, this 1 goes with 1, so I know those angles are congruent. 2 goes with 2, so I know those angles are congruent. By the third angles theorem, if two angles in one triangle are congruent to two angles in another triangle, then the third angles must also be congruent, right? So that might be helpful. Okay, something else. Yes, ma'am.
For the next, would you like add L and N together and subtract that from 180?
Okay, why not? Yeah, we know, if we know two of the angle measures in the left triangle, we could calculate the third pretty easily because they have to add up to 180, right? So 55 plus 65 is what? 120. So then how much is left over for M? 60. Okay, so if that's, if that's 60 degrees, now can we come up with a congruent, an equation maybe? So what's the equation going to be?
2x plus 3 equals 60.
Good. So we know that these two have to be congruent, so therefore their measures are equal. So, whoops. So 2x plus 30 equals 60, which we can solve pretty easily, right? What do we do to solve that? Subtract 30, divide by 2. So I get 2x equals 30, right? So what's x? Okay? Good. Okay, good job. Okay, this guy. Now this is, let's look at a proof here. We won't be real formal about this, but I want to see if we can prove something here. Our goal is that we want to prove some triangles congruent. Okay, now based on the markings up here, based on the markings, how many pieces, or how many parts of the left triangle are marked as being congruent to parts of the right triangle? Are marked. We will add some markings. Say it again. So the, okay, all the sides, right? So how many is that?
God bless you.
3. Now, how many total parts are there in each triangle that would have to match up? 6. 3 sides and 3 angles, right? Okay, we got all the sides. We can see that this side is congruent to this side is congruent to this side, and this side is congruent to this side, right? But now I got to get the angles. Because at this point, later on, we're going to have some shortcuts. That actually would be enough information in a few days for us to say that those two triangles have to be congruent by a little trick that we're going to learn. But for now, in order for us to show that the two angles are congruent, we have to show that all 6 parts of one triangle are congruent to the 6 parts of the other triangle. Okay? So we need some angles. Somebody give me, what's an angle that's congruent?
Vertical angles?
Okay, the vertical angles are, right? We know that whenever we have an intersection of 2 lines or segments, that the opposite angles are always congruent, right? So we get, right away we know that those guys are congruent. Anything else we know is congruent?
Because of the two angle, whatever, together.
Okay, so these are both 92 degrees. Their measures are the same.
So there's two angles that are equal now, so the other one has to.
There you go. So we know that these are congruent because they have the same measure. And by the third angles theorem, we get the third ones for free, right? If 2 angles from one triangle are congruent to 2 angles from another triangle, then the third one, buy 2, get 1 free kind of a deal. There you go, right? And now we're set. Now we've got all 6 parts of the left triangle congruent to all 6 parts of the right triangle. And so by the definition of congruent triangles, because that's what it means to be a congruent triangle, they have to be congruent. Okay? Good. Okay, what about this one? This is maybe a little trickier. Let's talk about this. Okay, let's prove that triangle AEB is congruent to triangle DEC. This is a little tougher. We're going to have to do a little more work on this one. So we're actually directly only given one thing, aren't we? We're only given one of the 6 necessary congruent parts. We need some more, don't we?
Is
Let's
it
see.
all equal because it's a square?
Well, okay, how do we know it's a square, though? It just looks like a square. We don't know it's a square, though.
Well, it has a full parallel
Okay, but it does have some information. Look what it does. It tells us, what do those arrows mean? Parallel. Okay, so it tells me that the top and the bottom are both parallel. So this might be useful. This is a trick that you can use too. I think this helps. When you have parallel lines, sometimes it helps to extend those parallel lines so they're easier to see. So I've got these parallel lines, and now what could I do with parallel? That's not a very good parallel line. What could I do with these parallel lines? We've talked a lot about when parallel lines are what? A lot of, like, chapter 3, we talked a lot about when parallel lines are cut by a transversal. Anybody see a transversal up here? Yeah, there are two of them, aren't there? There's one here and there's one here. Let's take them one at a time. Let's take, how about this transversal right here? If parallel lines are cut by a transversal, that tells us about some angle congruences. So can anybody find some angles that have to be congruent then? Alternate interior. Okay, so alternate interior. If this is my transversal, they're on opposite sides of the transversal inside the parallel line. So isn't that saying like those two? Right? Make sense? Okay, can anybody see maybe even an easier pair of parallel angles? Or excuse me, of congruent angles? Vertical angles, sure, why not? We've got two lines crossing, so we've got vertical angles right there, right? And then we get the third for free, right? So we've got this top triangle and this bottom triangle. We got two pairs of congruent angles, so the third ones we could prove using parallel lines and transversals, but why mess with it? We get them for free. So all our angles are taken care of. Now the sides might be a little trickier. Now they tell us something else here that maybe I forgot to tell you. Okay, they're giving us some information here, and this is an important thing. They're telling us that E, point E, is the midpoint of BC and of AD. Whoops.
BD.
Should be BD and AC. That's messed up, isn't it? Okay, so this is supposed to say BD and AC. So what? What does it mean that if E is the midpoint of BD, why is that helpful? What does the midpoint do? Cuts it into two equal or congruent segments, doesn't it? Right? So because that's a midpoint, can't I do this? Can't I say that that is congruent to that? Right? Because E is the midpoint of AC, it's cutting AC in half, right? I got it. Now I got all 6 pieces of the top triangle congruent to all 6 corresponding pieces of the bottom triangle, right? So I know they're congruent. Okay? Good. When are we out of here on Mondays? Never remember.
37.
Oh, okay. So we get a long time. Okay, so we got, so we did that. Okay, so then, here's what I was just saying. To prove 2 triangles are congruent by the definition of congruence, that means all pairs of corresponding angles and corresponding sides are congruent. In these upcoming lessons that we're going to talk about maybe some easier ways to do it, but for now, that's it. Skip that stuff, so we made it. How about that?
Yes.
Good. Give you a chance to...
I'm gonna go buy some things.